Thank you for the invitation. I remember being in a conference in Brussels, maybe 15 years ago, when Paul Zinjustin was working with Philippe on something and had to follow Philippe in a lecture, and he said, it's useless to try to imitate Philippe's inimitable style. And I should have taken his advice. So I will give some repetitions. I don't think you're getting a full screen. That's okay. Of what Philippe said. And hopefully this will not be a waste of time, because maybe you didn't quite digest the whole thing. So, but I will try to insert something new in here. Oh. Okay, not an ideal. Okay, let me try and change this. Okay, this is a combinatorics conference. And so I'll give you why this is a combinatorial talk. Maybe this will convince you, maybe not. But I'm not going to talk about any of this. So if you take a collection of finite dimensional representations of the affine algebra, any affine algebra that you like, but finite dimensional modules, cyclic, then Fagan and Loktev defined a grading on the tensor product of such modules. And so supposing that you believe that such a grading exists, you define the grading space. So these are the W of M will be the graded components of this graded tensor product. So I'm not going to say how this is defined, but the grading obviously is compatible with the degree in the affine algebra. And then you try to compute some polynomial in Q, which is the graded character of these things. So it's a polynomial Q to the M that keeps track of the grading. And then the character as a finite dimensional G module of the graded component. And these should be finite dimensional. So you're going to come up with some polynomial, which you can write down as a sum over the irreducible finite dimensional characters. So if it's type AN, it's just the short function, times some multiplicity K, which is a polynomial with non-negative coefficients of Q. And for example, if all these VIs are fundamental, not necessarily fundamental modules of G, but fundamental KR modules, so that they have highest weight, which is a fundamental weight for GLN, then this polynomial, which I call a graded character, is just a q-Whittaker function. And it's a limit of Macdonald polynomial. And we take the limit of Macdonald polynomial to be the t going to infinity limit. There's a duality, t going to infinity and t going to 0. And so that's one reason to call it a q-Whittaker function. It's known that you can obtain a q-Whittaker function from a Macdonald polynomial in this way. And in what sense is it a q-Whittaker function? Well, it belongs to it's a class 1 Whittaker function with weight corresponding to mu. So you interpret the variables x, Macdonald polynomials are some symmetric polynomials in x, as q to the mu plus the Weil vector rho that Philippe mentioned. And y is going to be, did I use y? No, didn't use y. So yeah, so q to the lambda, then it's a q-Whittaker function in these variables mu, right? So the quantum Toda Hamiltonian will act, as translation in lambda, but it's the variables x become the variables mu that correspond to the sort of highest weight, if you know anything. Yes?
But t tends to infinity.
Yeah.
So why right side has also parameter t?
I'll normalize it so that it has a nice limit.
Normalization.
Yeah. I'll give you the exact normalization in a second. And so this is the inspiration for our work that Philippe mentioned. And so this was our starting point, I don't know, 10 some years ago, 15 years ago, I don't know. Oh, this doesn't work, of course. Okay, so to recap what Philippe said without any beautiful pictures, let's look at this question in type AN. So here I insist that AN is an affine Lie algebra. So this is Katz's notation. Okay, so the spherical DAHA has generators which are the elementary symmetric functions in x's and in y's. I forget about the Hecke algebra. And their inverses. And the functional representation, which Philippe mentioned, acts on the space of symmetric functions in the x's in some field with rational functions in q and t in principle, where the elementary symmetric functions in x or their inverses just acts by multiplication by the elementary symmetric functions in the variables x, and the elementary symmetric functions in y will go to the Macdonald operators, which are q difference operators in x. And so Philippe already showed these. The thing to retain about these coefficients is that they're rational in xi over xj, which I can interpret as x to the minus beta, and they're polynomial in t. This is just a polynomial in t. You can expand this, and it's a finite polynomial. And so now I'm going to blatantly forget about the fact that analysis exists, and I'm going to define Macdonald Fourier transform as follows. So for example, the eigenvalue equation, the eighth Macdonald operator acts on the Macdonald polynomial as the elementary symmetric function in the variable s that Philippe introduced. So s is t to the Weil vector q to the lambda. So, and then this is the normalization that comes out here. And the solution to this, as Philippe mentioned, is unique up to normalization. And when lambda is an integer partition, if we normalize it appropriately, this becomes a Macdonald polynomial. Otherwise, it's an infinite series. But what I'm going to say with regards to the Fourier transform is that if I have some q difference operator in x, and I act on the Macdonald polynomial, or I prefer to act on the universal solution, in fact, by d, and I get some q difference operator in s, it's equal to some q difference operator in s, or lambda, acting on p, then I call this the Fourier transform of my operator d of x. So I'll have two sets of operators, d of x, and their Fourier transforms d bar of s. And like a good physicist, everything is assumed to be well defined. So I don't have to define integrals or anything like that. I just assume I have a complete set. And the duality, well, Philippe mentioned the duality as well. So if I define the p of x and s to be just some renormalization times the Macdonald function, then the duality relation takes the form p of x and s over delta of x is the same thing with x and s interchanged. X just keeps track of lambda. And the proportionality constant, I want to think of this as an infinite product over some positive cone in the affine root lattice, is what it is, of an minus 1, 1. Okay, so this we've seen already. And then as we saw, you can obtain the Pierre rule from duality. So if you start out with the eigenvalue equation, d1 of x acting on p is e1 of s acting on p, then I use duality to trade p of x and s for p of s and x. I cancel some deltas and shuffle things around. So I say that the dual of this equation is e1 of x, p lambda of x, is h1 of s, p lambda of x. So h1 here should be considered as the Fourier transform of e1. So this is my interpretation of the Hamiltonians. They're q difference operators in s, and that's what I'm going to call my commuting Hamiltonian. So I wrote the first one here for type an minus 1, 1. It's just this product that's just slightly more complicated than the Macdonald operator because I did some conjugation with deltas. And I use the notation t to be the q difference operator here in q to the lambda. So it translates q to the lambda I by q. Okay. In the q-Whittaker limit, everything is well defined if I just put in the screen normalization. So on both sides, it's the same normalization, so the eigenvalue equation has a nice limit. The Macdonald operator go to these q-Whittaker operators. I don't know what else to call them. They're not very much simpler than the Macdonald operators. They just miss one term in the numerator. But the eigenvalues simplify drastically because if you take the elementary symmetric function in S, the leading term is just the first term, you know, S1, S2, up to SA. And so that's all that remains when I take the limits t going to infinity. It becomes a monomial. So it's super simple. The eigenvalue equation has a simple right-hand side, a simple eigenvalue. Whereas the Peary rule, what simplifies in the Peary rule are the Hamiltonians. So if I take the t going to infinity limit of the Hamiltonians, this is well defined, and it's just this thing that should look familiar to, so it's a q difference operator in q to the lambda. And it is a version of the quantum relativistic GLN Toda Hamiltonian if you think about it as a difference operator on q to the lambda, not on x. And so, in particular, it's much simpler than the Macdonald operator. It's just a Laurent polynomial instead of a rational function. So that's why the q-Whittaker limit is simple. Nothing happens to the eigenvalue of, or to the Fourier transform. EA of x doesn't depend on t in this particular way of defining the limit. So these are the two equations that I get for the q-Whittaker limit. The eigenvalue equation has a simple right-hand side, and the Peary rule has a simple Hamiltonian. Simple in the sense that it's just Laurent. Okay, just to say, why are we allowed to call this a q-Whittaker function? It obeys, so this is a quantum Toda equation. So it means that this, the eigenvalue is a q-Whittaker function as a function in q to the lambda, because h is acting on lambda, not as a function in x. So it's a symmetric function in x, but not in q to the lambda. Okay, so then I have some commuting Hamiltonians, which are the Toda Hamiltonians, and my question is, what is the discrete evolution commuting with this HA of x? So this is the physics part, I think. I like to think of this as the physics part. So even if I don't go to the q-Whittaker limit, there is an SL2Z action on the spherical DAHA, or on the DAHA, in fact. And the translation operator T act in SL2Z, it's a theorem. It acts on the functional representation by the adjoint action of something that we call the Cherednik Gaussian. So it's this exponential of the sum of the log of xi squares. Okay, this shows up everywhere. So I'm just going to so that's why we gave it a name. So what it means is if you take the, so first of all, this is a function of x. So it commutes with any function of x. Commutes with the x generators of the spherical DAHA in particular. But it doesn't commute with the y generators. But it doesn't commute in a very simple way. The action on these Macdonald operators in the functional representation, the Macdonald operators had this translation operator in x, right? And the adjoint action of gamma inverse on t is just, it just gives you a q to the 1/2, and it multiplies t by x. So it's actually very simple. These translated operators, if you take the Macdonald operator and act with k times with the adjoint action of gamma inverse, you'll get some operators DAK, and they're going to look exactly like DA, the Macdonald operator, but they will have a factor of x to the k in front of t, the translation operator. So they look very simple. They're not very complicated. But because gamma commutes with functions of x, it means that the Fourier Macdonald transform of gamma is going to commute with the Hamiltonians. And so that is the motion that commutes with the Hamiltonians. That is the discrete evolution that commutes with the Hamiltonians, even in the Macdonald picture. And so the question is, well, suppose you wanted to compute this thing that commutes with the Hamiltonians. It's going to be some sort of generating function for Hamiltonians, and I'm going to answer this in the q-Whittaker limit.
And shouldn't gamma have a horizontal spectral parameter also?
I don't have any spectral parameter. What do you mean?
Well, if it were a transfer matrix that commutes with the Hamiltonian.
Yeah, okay. I will put in the spectral parameter in the end. Yeah. So in this picture, we don't have a spectral parameter. And so, a good question, how do you insert a spectral parameter in here in order to really have a generating function? Yeah. Okay, so let me first answer in the q-Whittaker limit, because this is where the cluster algebra comes in. So my claim is that this translation is, okay, it's just the q-system evolution. So what is a q-system? That's a cluster algebra. So first of all, I'm going to say it's the quantum q-system evolution. And I'm going to state the theorem that these translated D's in the q-Whittaker limit satisfy some recursion relation, which is going to look almost like this with the opposite multiplication. That's my statement. So first of all, I'm going to define g of lambda, some q-difference operator in lambda, by saying that I have these variables d bar of ak. I say that d bar ak is g to the k, adjoint action of g to the k acting on dA bar with no k. And I postulate that they satisfy these recursions without q. These are just the plain old q system, but without q, there is all the variables commute. But in general, the variables will not commute, and nearest neighbors in K, oops, I don't have my pen. Oh well, it's kind of a waste. What I wanted to write here is dA k plus 1 d bk, and then there's going to be a min a b up here instead of an a. It's more general. But nearest neighbors fail to commute with a min a b matrix. And then the q-system evolution is just a recursion. So if I give you the dA k minus 1 and the dB k, you can compute what dA k plus 1 is. So this is a two-step recursion relation, rational recursion. And I'm going to say that D is uniquely defined from this recursion, this operator G that I'm trying to compute, if I give you two initial values, so the values at 0 and the values at 1, so it should be sufficient. The values at 0, I'm going to take the eigenvalues of the q-Whittaker, the q-difference operator. So they're just q to the lambda dot omega a. So these are the eigenvalues in the q-Whittaker limit. And d bar of a at 1, at time equal 1, I'm just going to choose to be the simplest expression such that this q commutation is obeyed. Then G is uniquely determined, and by calculation, it's going to look like this. It's gamma of t being the, so if you'll excuse me for one moment. Oops, yeah. Take a breather. So maybe the only advantage of speaking on a tablet is that you can make corrections of typos as you go along. So this is B, oops. This is B, and this is min AB. And what was the other typo?
This is
q to the lambda. Q.
There's also a B in the first term in AB.
Thank you. Any other typos? Okay. So you can take the Cherednik Gaussian in this q difference operator T, and then times this product of q dilogarithms. And my claim is that this accomplishes this evolution. So you only need to compute 2 steps to see that the rest is accomplished by this. And you can take this operator, so it's in some completion of your quantum torus, and compute by hand that it commutes with your q-Whittaker Hamiltonians. And this, I claim, implies that G of lambda is in fact the Fourier transform of gamma that we were looking for. So this gamma of x. Why is this? Because you obtain that G acting on the q-Whittaker vector is the same, or function is the same as gamma of x acting on the q-Whittaker vector. And let's see, okay, I'm not actually writing down the proof. And you have to use the fact that this is then an eigenfunction of the Hamiltonian, because the Hamiltonian commutes with this side. So since the q-Whittaker function is unique up to a scalar multiple, the DAKs, the G is just gamma bar, and the DAKs then satisfy the same set of equations except with the opposite multiplication. Because of the Fourier transform, it changes the direction of multiplication. Okay, so the answer to the question I asked in the previous slide, which was what is the discrete evolution commuting with the Hamiltonian, it's the evolution of these translated q-Whittaker limit of the Macdonald operators. It's this cluster algebra relations. Okay, so the cluster algebra. Okay, there is the cluster algebra structure for this particular case. So it's associated with this quiver, where the D1, you can take DA0 on this side, DA1 on this side. This would be the quiver. So these Ds are A-type cluster algebras in the quantum cluster algebra. And the adjoint action of G, this translation operator, it just means, you click at these commuting variables, you get one time translation. You can call it a dent twist if you understand it correctly. And the theorem that I want to say is, so first of all, G is this product of mutations. Mutations are realized in the quantum cluster algebra by a product of quantum dilogarithm times monomial transformation. So the Gaussian part of G realizes the monomial transformation. So I claim that that's G, and also G, so this is to come back to Andrea's question, is an evaluation of something like a transfer matrix. So it's called a Baxter operator. I should call it a Baxter Q operator at some values of the spectral parameters. So there's two spectral parameters, U and V. And what is this operator? So you just extend my quiver a little bit. You put a little vertex here with a spectral parameter U, and a little vertex here with a spectral parameter V. And you start clicking on first of all on the rose. You start clicking in this order, okay? You get here. You notice that this is essentially the quiver I started out with some relabeling. And then you start clicking on the blue, you start clicking on the blue this way. You get back to the original quiver up to some permutation. These two quivers are isomorphic. So you have a sequence of mutations, and it depends on these two spectral parameters. You write down the operator QUV to be this product of mutations. So it's just adjoint action by some quantum dilogarithm times a monomial transformation. And the fact is that when you evaluate at U is equal to V is equal to 1, you get G. And so this Q is going to be the generating function, exponential generating function for the Toda Hamiltonians. Am I getting anywhere with time?
No, I'm telling you. You have 14 minutes.
Okay. Again, BC type DAHA. The generators are going to now be the Weyl elementary symmetric functions of x's and y's. I don't need to say x inverse and y inverse because they're Laurent polynomials anyway. So E1 is just the sum of the x's and the x inverses. Okay. And then in the functional representation, E1 of y, so E1 of x just is going to act by multiplication with x, and E1 of y is going to act by the Koornwinder operator, which looks like this. So it's a sum, it's a q difference operator in x again, first order. And now I have this rational function phi that depends on a, b, c, d, the parameters in the Koornwinder theory, and this, and t and q. So I have 6 parameters in the Koornwinder theory. So it's slightly more complicated. And then D1 is going to satisfy some eigenvalue equation with eigenvalue equation, and the eigenvalue is going to be sigma t to the n minus 1 times the first elementary symmetric function in S, where S is now, it's almost t to the rho q to the lambda, except it has this sigma in front. The eigenfunctions are going to be called Koornwinder functions. And they're polynomials, you know, if I choose sufficiently nice parameters. So again, I have duality. So there exists a normalization of the Koornwinder eigenfunctions, which I'm still going to call p of x and s, but they depend on a, b, c, d this time, such that p of x and s over delta of x is the starred version with x replaced by x, where star is this involution on a, b, c, d space. So there exists some involution like this, and so it's going to look like this. And this function delta is this infinite product, which includes the BC type roots. The Peary operators, I'm going to do the same game with duality. The Peary operators are going to act on P by the Weil symmetric elementary symmetric functions, but the Peary operator for type G is obtained from the G star Peary operator, Koornwinder operator, by conjugation by delta star. Again, star is just an action on the ABCD. Okay, and Philippe did show this table. So what I wanted to say about this table is that the q-Whittaker limit, I can't take the q-Whittaker limit of Koornwinder theory, at least I don't know how to, because the parameters a, b, c, d are going to scale with t. And so the q-Whittaker limit of h and d is going to depend on how a, b, c, d behave. And so, for example, in type D, I don't have any t dependence, but in all other types, I do have a t dependence. This notation R and R star is Macdonald's notation. So there are 2 finite root systems associated with each affinely algebra. Here, I use Katz's notation, and this is equivalent. There's a one-to-one correspondence between these pairs R and R star and an affine algebra. So R and R star are finite root systems. So affine Dn has R and R star as Dn. And affine Bn has R as Bn and R star as Cn. Affine Cn, it's the other way around. And the other theories shown here are self-dual. So you obtain Cn in 2 ways for R, one from affine Cn and one from affine A2n minus 1, 2, and the same for Bn. And A2n 2 is always a misfit. Okay, so for example, now I can take the t going to infinity limit, the q-Whittaker limit. And again, I get a Laurent polynomial for my Hamiltonian. So it's a q difference operator in lambda now. And so the notation here is, yeah, okay. I don't need to introduce notation. Lambda to the alpha I, so whatever alpha I is, lambda is considered to be a multivariable, lambda 1, lambda 2, and so on. Okay. Yeah, so I wanted to show here the roots that appear, the simple roots that appear here, these alpha I stars, they're the simple roots of the root system R star. So you're supposed to look in this column. So this is the Hamiltonian for the cases Cn1 and A2n minus 1, 2. So these two, they both look like type C, but they're slightly different because R star is different in those 2 cases. Okay. So discrete time evolution. What is the discrete time evolution that commutes with these Hamiltonians? And the thing is that For each affine root system, there is a quantum Q system. What is this quantum Q system? Well, the Q system is a recursion relation for characters of finite dimensional representations called KR modules. It was found many years ago by Kirillov and Reshetikhin, was then extended by Nakanishi and company, Kuniba, and various other people. I'm not sure what the most general. So Hatayama and the company wrote down the most general Q system. But it's just a recursion relations for finite dimensional characters. And the quantum Q system is the quantization of this. So this is what we defined. Yes. So in general, it's going to look, so if you're looking at where all the root lex, when R is equal to R star, essentially, this is what a Q system looks like. This is just the Q system, a classical Q system. So it's always a discrete integrable evolution in K. It depends on some Cartan matrix, which is of type R. And if A is not A2 and 2, this is a cluster algebra mutation relation associated with this exchange matrix. So the exchange matrix depends on C, the Cartan matrix of type R, and C star, the Cartan matrix of type R star. So it's always off diagonal. It has off diagonal blocks here, except if you're looking at the cases B and C. And so it has a canonical quantization as a quantum cluster algebra. So for example, Berenstein and Zelevinsky deformation. So we have a recursion relation for some non-commutative variables, which now I'm going to call Q hat, nothing to do with the Baxter operator. And they don't commute in precisely this way. So this time I wrote it correctly. So they fail to commute in terms of this, something that slightly generalizes the min AB matrix. These are fundamental weights of R and R star. And the mutation or the exchange relation looks exactly like in type A. So you exchange K minus 1 and K for K plus 1. It's Ka K squared and then a monomial in the neighboring elements in the thinking diagram. Okay. So the theorem is that we computed some Toda Hamiltonians by taking the dual to the Koornwinder difference operators, taking the q-Whittaker limit in the specialization for the parameters. And so these were what we called the Toda Hamiltonians. And for each one of these Q systems, they commute with the quantum Q system evolution, time translation operator G, that you compute in the same way as I showed you for type A. So the time translation operator acts differently if you have short and long roots. So if you have long roots, then it just goes K to K plus 1, but short roots are ill-behaved, it goes K to K plus 2. So when you have types B and C, there's a big headache, or type A2 and 2 as well. So in general, the spherical DAHA for Koornwinder doesn't have an SL2Z symmetry. It's some subgroup of SL2Z. So it either the q-Whittaker transform of the Cherednik, the q-Whittaker, this G of lambda that I compute from this evolution is the q-Whittaker transform, either of the Cherednik Gaussian or its square, depending on whether I have short or long roots. So the Hamiltonians are always elements in the upper cluster algebra. That is the Laurent polynomials in these variables Q.
You
Yes.
have 5 minutes.
I gotcha. Okay, so I'll say one word. How do you prove this? So first of all, you postulate a quantum Q system. We were given those because we know the Q system, we quantized them. We have other evidence for these being the Q system relations. We compute this time translation operator. We show by hand that it commutes with these Hamiltonians we computed for each G. Then you show that G acting on the q-Whittaker function, the eigenfunctions of these Hamiltonians, is in fact an eigenfunction of the Hamiltonian. Well, this follows by the fact that they commute. Therefore, it's proportional to the q-Whittaker function because the solutions of the Hamiltonian equation are unique up to a constant, and you compute the proportionality constant, and the proportionality constant can be a function of x, and in fact, it's either gamma of x or gamma squared of x. Therefore, we conclude, so that's how you prove it. So therefore, we conclude that the translated Koornwinder Macdonald operators satisfy the quantum Q system of type G, so some sort of quantum cluster algebra relation. And you can construct, so for example, how do you use this fact? q-Whittaker functions, pi lambda, you can construct them by acting with the translated operator at time 1 a certain number of times on the polynomial 1. So this is just a product of Q difference operators that actually commute, acting on 1. So what lambda is here, you just, it determines how many times you should act with each of these operators. The first one, for example, is a graded character of some KR module of the quantum affine algebra of G. But more generally, this product, if you just allow both A and K to vary, are just going to be these graded characters of the graded tensor product, the Fagan-Lochtef tensor product that I gave you before. And that was, in fact, the motivation for constructing all of this. Okay, so that's my last slide. So the Baxter operators, yes, there are Baxter operators for the other types. You draw the quiver. Here's the quiver for type D. Okay? You attach to it a spectral parameter in this way, and you start acting by going against the arrows. It'll stop at some point, and when it stops, you follow it around, it stops. That gives you a product of some dilogarithms, and that is, in fact, the Baxter operator, and it has a spectral parameter, only one this time, u. And if you evaluate this, you'll get your G operator. So this Baxter operator is going to be the generating function for the exponential, Q exponential generating function for your Hamiltonians. Yeah, just one last word. So at finite t, you might ask, okay, you still have a time translation that commutes with these Hamiltonians at finite for the Macdonald operator. So what is the G at finite t? So in type A, n, it's known. And for Koornwinder type, it's under construction. Okay, I'll stop here. Thank you for your attention.
Thank you very much for perfect timing.
With your help.
Okay, so now it's time for questions and discussion of this paper.
It's possible.
All right.
I have simple question because I remember I forgotten the lady who was speaking about dump operators.
Oh.
My feeling is very related, or how because I am not expert in this.
I think
I like harmonic analysis in that business. What was done in dump theory, but this is.
Should be very close, or.
So I thought in Duncan operators they're for non-symmetric theory.
It's non-symmetric.
And Charlie keeps saying that I should work on the non-symmetric theory, but I don't really know how to interpret it in my context. But I agree that there should be a relation.
I know there's some very nice lady in the Paderborn University when she made propaganda about Dunk, and she visited us in Poland, but now it's better theory, I think.
Well, I think the non-symmetric theory has its proponents.
Thank you very much. Beautiful.
Any other question or comment? If not, we thank the speaker.
Thank you.